Okay, so Roto talked yesterday, right? Yep. Yeah, so actually we are kind of joint team. So actually he was my PhD supervisor, and I have my own team. So anyway, yeah, Keio from Keio University as well. So nice to meet you guys. Okay, good. So basically, you guys love quantum networks, maybe, and quantum computers as well. And have you thought about the milestone of quantum networks? So actually, I believe like this. So as you know, some startup and so actually Quantium and QERA says that single node quantum computer, so FTQC will be realized by 2026 or 2029. So I believe that after that, the distributed quantum computers and the quantum networks will be more important because the quantum computers with quantum interconnect can scale very well after a single node quantum computer now is realized. And after distributed quantum computer is realized, then those quantum computers will be delivered to quantum data centers. And by connecting such quantum data centers, the quantum internet will start. So that should be 2033 or 2035. This is my expectation. So, project overview. So today I talked about our project on testbed effort actually is implementing the prototype of quantum networks. So our project overview is like this. So 6 years ago, so we established the researchers organization, so actually consortium, Quantum Internet Task Force here, and this task force works on quantum internet basically. And so Moonshot is a Japanese national project. And so now I serve as a project manager for the Shota Nagayama project. My task is to realize quantum interconnect for data center area networks. And so once a quantum interconnect is realized, so we can expand that network to quantum internet, so longer and heterogeneous networks. So there are different difficulties to realize, to overcome. And the Moonshot is the overall Moonshot program is like this. So my project is here to realize quantum network system and integrating all quantum system and classical system and the hardware and the software, everything. And there were other projects which works on hardware like superconducting qubits, ion trap, photonic semiconductors. And yes. Yeah. So later I will talk about quantum interconnect. So Q-Fly network we propose. So this is the overview of the picture of Q-Fly network. I will talk later. And this is my collaborators, so PIs actually, only PIs, but so now I will talk about on my research collaborating with them. So Roy is here, so you know Professor Kanemoto as well, and David is here. So Yasan is here. Yeah, is here as well. So they give talk in this summer school. And our project, so we start from data center area network. So our project, the concept one is actually a low area network that we will realize. So this star type topology network, because this type of topology requires routing, right? And so and the nodes should be quantum computers, and this should be quantum router or quantum switch. So actually, quantum switch or quantum routers are not well defined yet. So you know the classical switches and routers are well defined. So actually standardized in some standardizing organizations or documents. But from now, so we have to think about how to standardize those terminologies in quantum networks as well. So anyway, so now if we can realize this type of topology of quantum networks, so we can expand this network to more complex, larger topologies. And so of course we want to get so heterogeneity of networks as well. And so this is the concept one, and my moonshot project works on this. So lab area, so actually data center area network. And after that, so our plan is to expand our network to a longer distance. Now here, the concept is the campus area network. So our laboratory is placed in Tokyo area actually. And around the Tokyo area, so we have some places. This is Kawasaki City's incubation center. So we use that lab for our testbed, and we will expand our network to Keio University's campus. And for longer distances, so inter-campus network. So 5 kilometers to another Keio University campus or Yokohama National University campus, and throughout Tokyo as well. So there should be the University of Tokyo or other companies. My moonshot project started 3 years ago, 2022. But you know, to develop a quantum computer which has optical interconnect takes time, so long, to 2 years or 3 years. And it requires burden of experimentalists. So that's so hard. So we start from all optical network actually. So it's like so such quantum computer with optical interconnect is emulated by entanglement pair photon source. So the entanglement pair photon source, one photon goes to the quantum switch, let's say, and the other photon is measured right after generation. So but it emulates the quantum memory in the quantum computer. And meanwhile, so our project develops quantum computers, of course, with quantum memories and quantum repeating as well. And finally, so we will integrate our system to one system. So now the end node is actually quantum computer developed by here. And so network systems, so switches and passes between nodes are developed by this optical networks. Sure. So I say the testbed. So now here we have this kind of setup in our laboratory. So EPPS is entangled photon pair source, and so entangled photon pair source emulates the quantum computer. And there are node A, B. Well, where is C? She's already here. Yes. And so this is for a quantum plane of one node. And here is a classical plane of node B. So the controller is here. And so we need device driver to control quantum system from this classical control system. So we are developing such devices and drivers as well. And the node A and A is here. The model is here, design is here, node A is here, B is here, C is here. And this is actually the quantum switch. And the quantum switch is over here. And so, actually the progress of our this integration is going well, and we are publishing papers, and they are accepted to IEEE good conferences like Quantum Week or QCNC, and journals as well. So another view of our testbed. So switches are here. So actually, interferer is here. So beam splitter is here, and those are the switches. So optical switches to switching photons to choose from which two nodes we should make entanglement between those nodes. So we can choose two nodes by those switches. And optical delay line is here. So because of the timing difference and the photon comes into this node, so we need this optical delay line to make the photons interfere. So we have two pillars. So real testbed. So to implement quantum system experimentally takes time, and only small. So we can implement only small system. So we can evaluate our system with only small system. So but we want to evaluate the behavior of our system, the architecture, and the protocols as well in large scale network. So for the sake, so we have to conduct a simulation as well. So those two things, to have those things together is important to design the scalable and robust quantum network system. So what is a distributed quantum computer? So maybe you guys know about this. How many? So if we have a quantum computer with 10 qubits, now we have 2 to 10. So about a question.
2 to 10 is 1024. So 2 to 20 is a million times a billion.
Oh yeah.
That's a million.
Oh. Yeah, so this is the reason why we want to connect more quantum computers. Yes.
Hello? Can you go back to slide number 12? Right, so here you're working on the actual implementation. It's like kind of like a small scale system where the simulation is a large scale one. So I'm wondering, what are some limitations of the large scale system that you can't do yet in the actual implementation? Because as far as I know, simulations has some assumption.
Oh yes, of course. So the realism of qubits is only limited. So now we cannot use density matrix actually. So we want to simulate a large scale network which has so many numbers of qubits. So now so Pavliera simulator should be suitable for this kind of simulation. But so our simulator can switch multiple types of qubit simulation. So our design can evaluate our simulator itself as well with density matrix backend to compare with the actual implementation in the real testbed. Does this answer to your question? Thank you. Okay, and then I don't think I don't need to deep dive to this. So that's right. But distributed quantum computer, actually decentralization is important. So yeah, this is a large scale single computer, digital classical single computer. So there is so many cables to connect modules in a computer. So we want to avoid this. So of course, so the physical cabling is so hard, and there are data transferred in those fibers. So managing such data is terrible. So we want to avoid that. So this is one aspect why we want to decentralize quantum computer. And oops, sorry. And actually, in our project, now we are working on. So Professor Osada from Osaka University is working on developing ion trap quantum computer. Now, Monet is not here today. Okay, so okay, I see. So one student from Ronnie's group is working on this experimental setup of ion trap qubits, and she works on actually the engineering. So how to make ion trap quantum computer to engineering. So she's working on troubleshooting of the hardware of ion trap quantum computers actually. So so far the ion trap system is like system for experiment. But so this computer, so everything is engineered. So we have to make quantum system under such manage the engineering as well. And, so issues on implementation of quantum networks actually we are attacking in our real implementation. So the key issue one is entanglement generation and the quantum memory. So obviously high fidelity entanglement is required, but to manage that is really hard. And so retry and distribution, complex control is required to boost success probability and fidelity as well. And the quantum memories. So quantum memory stores entangled qubits with photons travel. And so the controlling the timing of photon emission and photon arrival is really hard actually. The time, let's see, yes, timing regime is here. So those are the typical timing regime in classical system. So TCP/IP message proceeding with like 10 to minus 5. And classical computers and software interrupt is 10 to minus 7. So classical data centers communication latency is 10 to minus 8. And this is a logic signal raising. Signal raising is 10 to minus 9. But in quantum system, so photon wave packet overlaps to make photons interfere is like 10 to minus 12. This is much harder than a classical communications timing regime. And so this is for two photon interference type quantum networks. For single photon interference, we have to manage 10 to minus 15 seconds. So this must be so hard. And the other timing regime is like, passive measurement. So basis selection of passive photon measurement is 10 to minus. No, sorry, this is wrong. So active measurement based selection should be 10 to minus 9. And passive measurement should be 10 to minus 3. And timing window for detectors, photon detectors is around 10 to minus 9 as well. And there are so many numbers of classical controlling part, right? So distributing routing tables between nodes is around here, so software tasks. Go back to here. So the key issue, and so what we need is kind of switches and routers. So dynamic multi-node links. So managing pitch quantum computers to communicate is the purpose of quantum switches or quantum routers. So switches and routers. So I mentioned switches and routers. So in definition, in classical networks, switches manages routing in one local area network, and routers manages routing between the other networks. So local area network belongs to one router. So the one router manages one local area network, and another router manages another local area network. And so multi-hopping between those different local area networks. So router works switching. So router manages routing, and inside one network, so switches manages the routing. So which two nodes to communicate. And how it differs from classical routers. So in classical networks, so copy and forward, store and forward, copy and forward works pretty well. And so if quantum compute, if classical data is not delivered properly, so we can resend the classical data, but in quantum, so, we cannot do that because of no cloning theorem. So for the sake, so in quantum networks, we do, so at first we generate quantum entanglement between two nodes, and then as execute quantum teleportation. And so low memory storing efficiency makes this problem harder. And the key challenge is to optical losses inside the switch reduce throughput. So switch is required for routing, but so switch itself reduces the throughput because they have some such optical things. Optical devices have so efficiency, so transmissivity. And marginal crosstalk and timing regime mirrors to handle many ports simultaneously. Oh yeah, so crosstalks and timing synchronization. So between two nodes, timing synchronization is not so hard. It is still hard, but it's not so hard. So, but there are so many numbers of nodes. So how to manage that? So this is challenging. So so we must co-design control protocols and algorithms and hardware for scalable switching. So there are so many components and algorithms, softwares, hardwares. So they have to work together properly. So that's why we need to implement prototype to evaluate overall system of quantum networks. Simulation is not enough. So implementing prototype is important. Quantum switches and quantum routers. Oh yeah, so those are the same slides. And yeah, so so we do so memory interfere, memory type link. So maybe Rod mentioned this, right? So for this interference, so as I said, this timing control is important. And so this is a easy overview of our testbed implementation. So the blue rectangles are quantum part, so quantum plane, and the red are a classical plane. And so they are collaboratively generate entanglement between two nodes. So actually there should be another end node B or C. And after generating entanglement, so the control of entanglement is passed to application. Then application use that entanglement. Yeah, to make interference happen, so their mode must be same. So not only timing, but also the polarization, the spectral modes, the temporal modes, the arbor time, and transverse spatial time. If we don't have enough accuracy, so the fidelity gets worse. good fidelity is high visibility. And so yeah, this is good timing. The photons comes in together at the same time. This is bad overlap of photons. So this one, the interference doesn't occur. So even if it happens, so the fidelity gets worse. So the key issues we quantum correction and the threshold. So the so the fidelity gets worse easily. But quantum computer has quantum error correction, and we can use a quantum error correction technology to manage errors even in quantum computer quantum networks, because the end nodes are quantum computers. But still, the problem is like, so the fidelity of qubits, so those communication qubits must be higher than the threshold of error correction, so error management scheme. And so large heterogeneous latency between nodes and heterogeneous, so error rates between nodes, so negates the error correction gains as well. So we have to make good design to overcome those problems as well. So we have another requirement. The requirement is different from single node quantum computer for quantum error correction. And distributed system factors, so layer delay, link delays are non-uniform between across nodes, and each switch hops as latency and photon loss, so reducing throughput. So design goals, so distributed CPU system architecture that accounts for link success rate and switch delays. And so jointly optimize software protocols and hardware implementation, so many modules. So those are design goals. Okay, so here are quantum networks. So many times I mentioned classical plane and quantum plane. So the quantum plane is here. So quantum computer node, so those are connected by quantum networks, quantum system area network, let's say. So system area networks, this term comes from the classical network. So system area networks is similar to data center area network. So there are multiple nodes, but still, so this is a distributed system. So they work together as a single system. And there should be quantum computer node, quantum storage node we may have. So the quantum memory node and the quantum network interface card. So maybe this quantum network interface card will be the interface to longer area network. So longer link to another data center as well. And so those quantum system, each system has quantum computer controller or quantum storage controller or quantum RAM controller. So they are also connected by a classical network system. And this is a system layer network overview. And so what composes quantum networks? So classical case, so there are the classical electronics, optics, and controlling engineering and physical properties. And over that, so informatics field, so maybe architecture field, we can say as well. And this, communication theories and engineering and engineering encoding, so network engineering, so protocol stack as well, and software engineering. So not only hardware, but also the software engineering, like how to make operating system of quantum computers with networks. And network theory as well, so distributed algorithms and applications. And so beyond that, we have use cases. And in quantum case, so everything changes. So we need new things. This quantum physics, so the classical physics changes the quantum physics, quantum electronics, quantum devices, quantum optics, so optical properties, and nonlinear optics, so as you know. And so this here, so those quantum memory technologies or quantum photon interference technologies, so phase adjustment, so noise mitigation, so quantum frequency conversion, and quantum repeating, so those are included here. And so beyond that, we need protocol stack. So with those physical technologies, physical layer technologies, so we need, so we will implement link layer protocol. So the physical layer protocol, so there is efficiency and it's not deterministic. So at some point, so we need deterministic entanglement generation. So I mean, deterministic not in physical, but logically, this is deterministic. So now, if the upper layer protocol requests entanglement generation, so at some layer, so that layer should answer, okay, here is the entanglement you want. So, so this means reliable entanglement generation. So some layers should have this reliable entanglement generation responsibility. So now some groups proposes such reliable entanglement generation should be guaranteed by a link layer. Some groups proposes that should be guaranteed by the transport layer. So there are multiple proposals. So, but it's not decided yet, which is best. So actually, this is design principle. So there should be many theoretical works, and so the standardization organization will discuss this architecture. And so this is corresponds to TCP/IP of classical networks. And so we have to implement those protocols for our test bed. And there's applications and use cases at the purpose of quantum networks or quantum internet. Is beyond that. And so what's needed? So implementable design. So beyond those things, we have to need to make implementable design. So here is some details of the protocols of each arrows. So here, so the quantum memories will emit a photon and quantum memory here as well. So those photons may have 2 photon interference or 1 photon interference. And the switching system chooses which 2 nodes. Now there are 3 nodes. The which 2 nodes to generate entanglement between. And here's the protocols close to quantum physical layer. So maybe this time critical protocol should be handled by FPGA, so hardware processor. And so like the like telling the heralding signal from the BSA beta state measurement node to end node. And yeah, this is time critical. And other information like, so which nodes is connected to by which link, so such kind of routing table information can be handled by computer, which is much slower than the hardware processors. And so we need also synchronization between those two systems. So, here in quantum channel, so photons are repeatedly generated by many quantum memories. So for multiplexing purpose, then we have to distinguish which memories get entangled with which memory of other nodes, of which nodes. For the sake that timing synchronization is important, and this kind of the synchronization channel is required. And so actually, so often this is called quantum plane, and this is called classical plane. So this is from software-defined network in classical networks. So now, when we use internet, so as a user, so control plane and the control messages, control information, and the data information is delivered in one channel. But in classical and software-defined networks, so now there are architecture in which actual data is delivered in data plane, and the controlling data is delivered in control plane. So quantum networks is actually resemble to these software-defined networks. And then we have to implement classical internet layers. So we have to design those layers, physical layers, data link layer, network layer, so transport layer on this system. This tells only the connection between modules. So we need to design and implement communication protocol on this. And so many proposals which runs from classical networks have been proposed. And this is the design for implementation our network case. And so blue are quantum plane, and red are classical controlling plane. And so blue arrows means a quantum signal, and this dashed signal means analog classical signal. So analog signal, and the red arrows are digital signal, and this dense dashed line means TTL, transistor level, logic level signal. So there are so many channels between nodes, and even in one node as well. So they have to collaboratively work properly. So here, so when one request from application happens, so at the first classical plane, so reacts to the request. So the connection manager, this entanglement request is issued by application. So this entanglement should be generated with this node or this node. Then connection manager manages the scheduling of the entanglement generation those two. So okay, now can we get a time slot of this quantum switch node? And such scheduling happens and after that, okay, so then we need a rule to generate such entanglement. So rule generator works, and the time slot assigned starts. Those rule engines start to work for that rule. So individually, but of course they collaborate. And those rule engine manages those quantum hardwares through quantum resource manager. So hardware monitor is actually for the health check of those quantum hardwares. So So quantum hardware monitor finds like the fidelity gets worse. So then we have to adjust something. Like polarization is somehow changed, so we have to fix that polarization. Or timing is different. So now the timing doesn't overlap well. So we have to readjust, so calibrate the timing. So hardware monitor is important for this quantum resource manager. And those resource manager, so until here, this is software. And FPGA is for real-time controller. So it manages so qubits, a signal one. And yeah, in the node, and a signal to control qubits. So now through arbitrary wavelength generator or laser modulator. So and those communication qubits then emit a photon to switching node. So the same things happen in the another GS's in the node, and photons are emitted by communication qubit, and they comes in the switching node, and so those switching node chooses which two nodes to get photons from for this rule. Then those two photons the timing is adjusted here by this optical delay line. So then those photons go into this beam splitter together at the same time, and polarization beam splitter is here for Bell state analyzer purpose. And and this FPGA finds optical entanglement swapping happens or not. And so this is the heralding signal, and this tells the end nodes so the success or fail of the entanglement generation. But actually, I say, so we use only just emulated quantum computer. So we use entangled photon pair source for end node. So slightly the design of the end node is different, but the switching node, so they are the same. So for this purpose, we had to develop device drivers to control devices in quantum hardware plane. So this optical delay line and the polarization rotator to decide to calculate the polarization of photons comes into this switching node because in this path the polarization may change. So depends on so this path optical quantum signal path is implemented by an optical fiber we are using today, and so the polarization of photon changes easily. So and actually, if we touch the fiber, the optical the polarization of photon changes. So every time, and so the wind from air conditioner is also affect the performance of quantum networks. So we need polarization controller, polarization compensator. So in this node as well, but actually in this figure they are omitted. So like that, so we need not experimental system, but the reliable device controller, so device driver to make those overall system as a reliable quantum computer network system. And plug and play quantum is that device driver we developed. So now they are in open source, so you can access and get our software implementation here. And now they support Solar's devices like optical delay line and polarization compensator. And we are expanding the vendor of those devices. So in our system, they are used here. So optical delay line, a quantum switch controller, and here should be polarization compensator. TDC toolkit. TDC means time to digital converter. So I said, so we need accurate timing regime control. So even for two photo interference system, so 10 to minus 12 second has to be managed well. So this time to digital converter toolkit supports such timing stamp functionality. Now this supports so multi-hop time stamp producer, so, which is provided by Pico Quantum, and so we are expanding that as well. And actually, we are developing so our self-developing so timing hardware system, so which only uses FPGA. So timing synchronizers. So they are used here, timing synchronizers or time resolved measurement. And so those devices can be supported by our open source tools. So you can use if you have enough budget, if you can buy the quantum devices, so you can so you can build your own quantum network system using our quantum device drivers. And so device driver is only device driver in one node for one module. So beyond that, so you can implement your own quantum network protocols or architectures as well. So this is open source, please use that. So they are on GitHub. So rule set protocol, yeah, so I think Rod mentioned the rule set protocol with this slide. And so those are here. So rule set is here, rule engine is here. And so yeah, this system can be expanded to 4 more hops. So yeah, this quantum computer can be connected to other switch as well. So this quantum switch can be connected to other switch as well. So by such expansion, this kind of rule set based protocol acts very well. And yeah, so now, so here quantum repeaters. So if this quantum, so this node which has qubits, so memory qubits has more hops, so more links. So this one works as quantum repeater, and so it can handle quantum repeating, and so rule set based protocol. And this should work. And so our network protocol design is also available on GitHub as well. So here is an initiator, and so BSA1, and the quantum repeater BSA1, so responder. So this is like that. And the classical message is relayed by initiator to responder, and responder makes the rule set for every node between those initiator and responder. So they distribute that rule to those nodes, and finally, at one time, and at a time slot begins, so the rule starts to work individually but collaboratively. So timing regime document is also available on our GitHub page. So this is a kind of the specification document. And some of our scheme of our specifications are available on GitHub as well. And so specifications of the endo node or quantum repeater node or BSA node, so everything. And in the so emulated version, so all optical system networks. So our open source tools can be used those things. So we will create a rotator, so timing signal, polarization compensator, so optical delay line and the switches. Okay. So far, this is a design or implementation, and so QFI network is actually a quantum interconnector design for data center area network, so distributed quantum computer. And so I will talk about the overall design of QFI and also the actual implementation of those designs as well. But now, so 15 4 minutes has passed, so I would like to have 5 minutes break. Okay, so now we should resume 3:30. Thank you. If you have any questions, you can ask. So between break.
I have a couple of questions.
Yes.
This is not simulation, right? So it's
Yeah, simulation is used.
how do you plan to connect more than 3 objects? Because at a level, because do you like void rabbit or?
Yes. Now we conduct all experiment in one room. So actually, we can skip this synchronization, but so we plan to use white rabbit to expand our network.
Also for
Yes.
Also for the feedback loops, it depends a lot. For example, when you're doing something experimentally, the commands that you need to send depends a lot on the manufacturer, right? It's right now just the logic, or and then you can input the IP address and the instruction separately, or how does it work?
Feedback loop between what? Could you say again?
Yeah, for example, if you want to have the optical delay line, or
Optical delay line here, yes.
Or you want the switch, for example, you have a feedback loop, or you have
yes, no, we have feedback loop.
So, for example, when you want to control a physical device, they have instructions that depend on the manufacturer. So right now it's just the logic behind it, or it's a bit more general, or for.
So for the feedback, so to see the success or fail of this optical delay line adjustment, we have to check the Hong-Mandel. So we have to check the interference occurs or not by the measurement result by this SSPD superconducting single photon detector. So the optical the feedback loop happens like, okay, this delay lines changes if the interference success or not. If not, we have to adjust this optical. So we slightly change the optical delay line, then check the interference occurs or not again. So this is a feedback loop we have.
On the slide earlier, I didn't quite understand. There was something that had a femtosecond timing reference, like phase stability or something, you said.
Oh.
Does that mean you need to agree on a femtosecond across these nodes?
Yeah, so yeah, single photon interference is sensitive to phase difference. But now we have only two-photon interference implementation. So our system is not sensitive to the phase of photon yet.
So that's just changing at that speed, but you don't need to control it.
Yeah, so we don't need to have the phase stabilization in our system yet. So if we expand our system to single photon interference network, so we have to care phase stabilization.
So what clock reference would you use for these to keep these nodes synchronized? What clock reference do you need?
Sorry.
Well, is it a gigahertz clock you need to agree on, or do you need more precision than that?
Now, so actually, our single and EPPS. So let's see here. Our photon pulse generator generates the optical pulse which goes into EPPS crystal in 1 gigahertz. In that sense, 1 gigahertz synchronization is required to distinguish which photons get interfered in this PSA node.
Also with the switch in the central node, the Bell state analyzer, do you know how much loss you can tolerate or how much loss there is there?
How much loss?
So from the delay line and the switching?
So loss here, so overall loss rate is like, so it's like overall loss rate is 10 to the minus 7 or 10 to the minus 8 now. So that we don't distinguish the loss rate efficiency of this BSA node is not calculated yet. So on the overall now 10 to the minus 7 or 10 to the minus 8 efficiency.
There is some budget, so the papers on the archive, and then there's actually some details on the some of the loss budget details on the archive.
Yeah, actually.
Those numbers change as we improve the implementations, the alignment structures. There's some details, this switch was that many dB, that switch was that many dB in the draft, but those numbers should be taken with a grain of salt because they change.
So my question is actually like this kind of software defined networking, many people are doing it, but you are actually doing it on the real quantum data set.
Yeah.
Is this data set available online or like can it be available?
So in the dataset,
For the actual quantum network?
Dataset is not available. So
Like-
we only the implementation of our software is available.
Okay, so can it be available? Like because there's no actual data set for quantum test beds available. I don't know, might be due to some security reasons or something. But
Yeah.
Just the numbers that go into calculating the density matrices are probably fairly readily available. But if you wanted the more detailed data set of when the detectors click, that's tens of gigabytes for every single run.
okay, but for the different networks like KDL and stuff, there are like 794 nodes with constraints and everything. The data sets are quite very large. So if a data set for a quantum test bed is available online, I think so it will be great improvement for overall community. Because there is no test, no available data set. So we usually take classical data sets for networks and assume some quantum constraints on them, and we do the work. That will be quite an improvement. Like.
I don't think we're prepared to make a total of hundreds of gigabytes of data available over the net right now,
Well, for
that's an interesting idea.
Yeah.
I'm not sure how much documentation and how much other qualifiers would have to go into all of this to make the data actually useful.
Yeah, because for machine learning algorithm, it doesn't matter. The more the data is better. So, thank you.
Yeah. So I agree your opinion. So yeah, it must be interesting. But yeah, we have to think about the feasibility of that idea.
Standard protocol and stuff that would be good because maybe I'm also working in software designing the so there's no data.
Okay.
Thank you. I was just wondering about this toolkit that you have for your taggers. What's the difference between this, your toolkit, and the Snappy package of the PicoQuant itself? So what made you to make your own toolkit, basically?
So now you need PicoQuant and PicoQuant as a multi-hop, so timestamp. So this toolkit is for software side.
Yes, but they also have this snappy packages with APIs, and you can do all of your coincidences, correlations, measurements, and yeah. So I was just wondering.
It's not open yet, but yeah, we will provide it available.
Okay.
We'll make it available.
Thanks.
Yeah, so I understand this is mostly for distributed quantum computing. So one question I wanted to ask is, in this design, with this rule sets to control the nodes, do the nodes have any autonomy, or are they fully controlled by this rule set and the central controller?
Oh yeah, now so we can say so. Now our implementation is the centralized controller type. So in the data center area network, so everything should be able to be handled by centralized controller. But for quantum internet, so everything has to be so decentralized, so managing scheme.
The rule sets execute at the individual nodes, so each node will have its own rule set for one connection.
Yeah.
And the goal is for those rule sets to enable the node to operate as asynchronously and autonomously as possible, consistent with the goal of making the end-to-end entanglement.
Okay.
So it's a framework for doing that. And then if some individual wants to come along and propose, I think we should do these things in this order, or you can relax that constraint on another, in another way, then you can write a rule set that implements that way. And that's the goal. So it should be a mechanism to allow us to explore a bunch of different policies. And in the two-pass setup that's illustrated up there that I described yesterday, the responder is the one who decides what those rule sets will be for all of the nodes along the path for that connection. But then there might be another connection going in another direction, or even a different connection between the same two nodes could have different rule sets defined for each of those. And so the policy that's actually implemented there, we think this mechanism provides a lot of room for innovation.
Okay, so the rule sets could either be defined like a central controller, or they could be defined a bit more independent.
Yeah, so in the data center network that we're building right now, the rule sets are defined by that central controller, and in the distributed internet, they're defined by the responder at the end of that setup.
Okay, thank you.
Yeah, actually, the purpose of rule set is to reduce the number of messaging between nodes. So the rule set, so predefined behavior is defined in rule set. So they don't need to negotiate every time. It's 36. Okay, I don't have break. Let's continue. So now I will talk about our quantum interconnected design and actually the implementation, prototype implementation of our networks. So there are actually this is a two-level system. So this is like a local area network, and those local area network are connected. 5 networks are connected here. So actually this is like a quantum link, or so link switch design. So there are communication qubits, and then the switch is here, the BSA is here. So actually this is a quantum link prototype implementation. And of course, this switch can manage which two nodes can connect. So this is like a classical link, classical Ethernet link, and a classical Ethernet switch. So Ethernet switch can control which two nodes to connect by that Ethernet link. And so this is a kind of local area network, and here we say group switch in this Q-Fly interconnect architecture. So yeah, this is called a group, and so this switch manages this group. And so in this group, so there are quantum computers here. Those rectangle box are quantum computers actually, and here is a series of BSAs, and here is a quantum switch, and this is a group, and 5 groups are connected, and those 5 groups are so free connected. So those switches are free connected. So this is why this Q-Fly interconnect design scales. So I will talk about that. So yeah, at the beginning of our project, we start from, so our idea started from tree topologies actually. So you may know fat tree topology of classical supercomputer network. And so here are quantum computers and quantum switches and the BSAs. So, but this topology, so as I say, the quantum switch has transmissibility. So if we have more quantum switches to go through for a photon, that photon has so lower efficiency. So this is a problem of tree topology actually, and actually from 2012, I believe, so a dragonfly topology was proposed in classical networks, classical supercomputer interconnect architecture. So this dragonfly network has so also it was the same design actually. So they have switches here, and the switches manage so each switch, so multiple so end node computing nodes belongs to a switch, and those switches has fully meshed connectivity between switches. So by that, what happens? So end node can communicate with every other computing node only with 2 hops. So okay, from here, the first hop, this is switch of that group. The first hop should be the switch of that group that end node belongs to. And the second hop is another switch. And the third hop should be the computing node to communicate in purpose. And so they have, in dragonfly topology, they have fixed hop counts to communicate. So this helps the latency. This helps reducing the effect of latency. So actually, this helps the efficiency problem of photon loss in quantum networks. So our group developed a Q-Fly topology, Q-Fly interconnect network. So after this dragonfly topology, oh yeah, by the way, now the dragonfly topology is employed in 819 supercomputers, also all over the world now. So the classical supercomputers is updated every 10 years, maybe 7 or 8 years. So the first proposal of dragonfly topology was 2012. So it's only 13 years old, but so now 819 supercomputers has employed dragonfly topology. So yeah, this is good. And so this must be good for quantum computer network as well. Why? Because of the...
It's okay, good question. Why quantum mechanically?
Quantum mechanically. Oh yeah, so if the numbers of the quantum switches go through increases, then so more just smaller the total efficiency from one node to another node. And so if this tree topology gets larger, okay, now this figure only have 2 layers of switches. That's 3 layers, 4 layers to expand as a quantum computer system. So then tens of switches a photon must go through. Then the efficiency gets lower and lower. And between the quantum computers, to make communication between quantum computers of the apart in topology. The throughput must get so slow. So this is a scalability problem in tree topology of quantum networks. So yeah, of course, if we have a quantum memory in those switches, so now it helps because we can execute quantum repeating, but the quantum repeater must be much expensive than only the quantum optical switch node. So from the total performance, so cost performance point of view, so this optical switches should be more better than quantum repeaters. But yeah, so it depends on the how many hops we should have. So how many quantum computers we should have in one quantum data center. So it depends. And let's see. Yeah, here, okay, now there are two quantum computers. So each quantum computer emits a photon. And okay, this photon suffer from the loss by this switch. And this photon, another photon, suffer from loss from this switch as well. So in total, two potential loss is here to generate entanglement between those two quantum computers in one group. So across groups, the photon, okay, now this computer and this quantum computer, and let's use this BSA node. Then a photon emitted from this quantum computer goes through this switch and this switch. So there are two lost chances, and a photon emitted from this computer has one photon loss chance. In total, 3 photon loss chance. So that is this is loss chance across different groups. And okay, let's see. Let's have communication between this group and this group. Yeah, obviously, in total 3 loss chance as well. This group the same 1, 2, 3. So yeah, so this is the same even if we expand this Q5 topology with more number of groups. Now we have 1, 2, 3, 4, 5 groups. So even if we have 10 groups or 20 groups, so the number of the photon loss chance is fixed, only 3. So this is and this is why we think Q5 topology should be scalable in quantum networking. And so in our prototype implementation, so we implement a group switch here. So we have a prototype of one group, and here is a switch, and here are 3 emulated quantum computer nodes. Those are the photo of the each node and the switch. The 3 SPCD nodes, and the switch is the switch node is here. The switch optical DA line, the interferer, and SSPD. And so we can see the Hongo Mandel dip of the BSA. So the x-axis here is actually the optical delay, the parameter of the optical delay line. So here interference doesn't happen. Here interference doesn't happen as well. But here the interference happens. So for the feedback loop, so we have to see this Hongo Mandel dips are changing. So to see if the optical delay line setting configuration is good or not. So our first time experiment of this setting, actually the fidelity of each node, fidelity of entanglement of each SPDC node generates is between 88% to 95%. But the internode bell pair, so internode bell pair, I mean, so here one photon from here, one photon from here, the optical bell state measurement happens, and so finally, remain the two photons get entangled. The fidelity of those remained photons, the entanglement is like 60% to 70%. So this is because not so good adjustment of the settings here, so optical delay line or polarization compensator. So we are working on to improve that. So actually, every time we change the configuration of the quantum switch, okay, so I mean, at first we execute entanglement swapping, so the entanglement generation between this node A and node B. Then we move to generate entanglement between node B and node C. So this will break and newly make a new optical path between two nodes. So the reconfiguration is really important. Reconfiguration and so adjustment of optical path is really important. But the first result is not so good. So and actually in this first experiment, polarization compensator was not automated, so it was fixed. So now so we are replacing the polarization compensator with automated one to improve this fidelity. And yeah, and also we start from type 2 SPDC, and we replacing the crystal for SPDC to upgrade to type 0 SPDC source. So it will improve our fidelity. It should improve our fidelity as well. And so performance evaluation of our, so performance, I mean the performance in distributed computing evaluation. So actually this is estimation of performance. Now there are parameters, network parameters like, so how many groups we have is G, parameter G, how many quantum computers that belong to a group is P, and how many radix a switch has is K, and how many BSAs one group has is parameter B. So there are so parameter space we can choose, and the total number of nodes is N, and the total number of BSAs are D. And so to evaluate a Q-fly network, so we estimate, so we employ QFT, quantum frequency, no frequency, Fourier transform circuit, and we estimated the how much steps we need to execute a quantum frequency transform by simulation, by a software. And let's see. And so this red line is a kind of baseline to evaluate. So this red line means, so we can develop an arbitrarily large scale of quantum computer, so which doesn't need a quantum network, so distributed quantum computation to execute a quantum program. So in this case, a quantum frequency Fourier transform. And so this tiling means, so each node has a limit of size. And so they are placed like tiling. So lattice style topology. And so this tiling requires 5 times time steps to execute a quantum Fourier transform compared to this baseline arbitrarily large size quantum computer. And those numbers from 1 to 6 is actually a kind of configuration of Q-Fly networks. And we find that some configuration, the Q-Fly networks has better performance than tiling. Yeah, so this is a good signal of that. So the design of quantum interconnect will improve the performance of the distributed quantum computation. So we tried only some particular configurations. So we are expanding the parameter space now. So okay, this is a kind of overall design. And so let me introduce some individual results which contribute to quantum networking. So now this is a quantum switch chip design actually. So this is by first author is Mari Koyama. So over there, raise your hand.
That's not raising the hand.
So yeah, this work is conducted 2 years ago. So when she was third grade student, right? Second year student of undergrad. So it was presented in IEEE Quantum Week. And in classical networks, the switching design is like this. Quantum switch is a switching module. They have a switching module inside. So there here, let's say, 8 nodes are connected to that switch. And the left side is input, the right side is output. So we want to route all the from arbitrary input to arbitrary output. So it's like this. So this is a classical case of switching module in switches. In quantum case, so we have to pairwise photons. So this is a different design principle from different from a classical case. So we need dedicated design for quantum switches. So she found optimal design for this switching. So actually, those small box is a 2x2 switch, and from 2x2 switches, so the overall switch design is composed. And what is good here is actually now, so okay, here one pairwising, this red one. So this connects quantum computers connected to X1 input and X7 input. And actually, so another connection can be executed at the same time in this design. So and this is called non-blocking characteristic in switching design. So actually the blocking design, so yeah, only one pairwising can be performed at the same time. Oh, now, okay, now we are executing this red one, so a blue one cannot be executed. other connections as well. So such blocking design is very easy. But this non-blocking design, so now we have only two, but so we can have green, the third one, the fourth one, let's say yellow, all of them can be executed together at the same time. So this helps improve of the performance of quantum networks. Yeah, it's interesting program in networking actually. And oh yeah, so then she found the non-blocking design and the minimum number of those small 2x2 switches. Correct? Okay, confirmed. And Joshua was there, yeah, David's group, and so we can imagine the result by Joshua. So to Q-Fly network as well, and so Joshua's result should be presented by poster maybe or later this week. Will you present? So yeah, this session, this summer school has poster presentation, right?
Yes.
Okay, he will present. So yeah, then he will talk about that. But his scheme helps the health check of quantum networks very well. And so such kind of health check mechanism, of course, should be implemented in Q-Fly networks as well. And we can implement that. So once we achieve connection between quantum computers. And so his work is really theoretical, but so you can imagine, so even theoretical work, so how theoretical work can be implemented in actual quantum networks. Is Kai here? Maybe not. So yeah, people from Kai's group is working on the link aggregation of quantum networks, right? And so link aggregation, so there are two nodes, and there are multiple channels between those two nodes, and how to help how those multiple paths helps the quantum communication between two nodes. So their work is that, and there's a performance analysis of that. And actually in the Q-Fly network, so now we can have multiple channels between same nodes. So now this node and this node, I mean the computer node, so they have this channel and this channel as well. So now we can use two channels. So the throughput should be twice compared to a single channel. So we should be able to implement their idea to Q-Fly network as well. Soon, hi. Okay, you raise your hand before I say. Yes, since work compares actually, so he compared memory interference, interferer memory type link and memory source memory type link. So memory source EVPS is here, and the memory is here and here. So now theoretically, so it is discusses that. So the require so if the small number of memory, so quantum computer node may have multiple quantum memory communication qubits, and if we have small number of communication qubits, so it is told that memory source memory type link has larger performance compared to MIM type link, and he checked. So this is only theory, but he checked. So even if we have the quantum network protocol, so not just a theory, but now protocol engineering happens. So even with such protocols, and so there should be overhead by such protocol engineering, but still, MSM type memory has larger performance than MIM type memory in the parameter field of memory. Number of memory is small. So this should help. So connection, this should help. So if we connect two surface code quantum computers, so now for each stabilizer, so for each stabilizer, we have only one communication qubit or two communication qubit, so not so many. So in such parameter field, yeah, this type of link architecture may help. Soida-san. And so Professor Soida, he will give talk. You will give talk here? But not on this one. Yeah, so now, actually he is now making an evaluation scheme of single quantum computer node. So if it can execute a distributed quantum computation, even with one node. So if we have two nodes, so it can easy to evaluate. So this distributed quantum computation is executed properly or not. So his idea, so only one node, so we can evaluate that. So this kind of work will help the quality assurance of future quantum devices, future quantum computers. So this is theory, but it will help the engineering of the production of quantum network nodes. Yeah. So this will help the quantum interconnect QFly as well. So yeah, mostly I talked about the data center area network, and we are working on the long distance communication as well. How to expand our data center area network to long distance network. So here is Shin Kawasaki. So our laboratory is here, and here is another campus, Yagami campus of Keio University is here. So now long distance phase stability, so management work is conducted, and as well, but we haven't tried to send a photon from here to here yet. So yeah, we will do that as well. We will expand our network. And theoretically, we have discussed what is the requirements to be a quantum internet. So so this is a kind of the standardization related work. So I believe at least those two characteristics are required. So the arbitrary quantum data should be must be able to be transferred, and so arbitrary distributed quantum application has to be supported by quantum internet. And the quantum interconnectivity. So the quantum network, so each individual quantum network will be developed with different technologies, heterogeneous technologies. So even in such condition, so they have to be connected with interconnectivity and interoperability. Yeah, those two things are important requirements for quantum internet. So before that, so we have published RFC. So RFC is a document, kind of a standardization document published by IETF. So IETF standardize the classical internet protocols and architectures. So the TCP/IP of the classical internet is also standardized in IETF. And quantum internet case. So here in IETF, so actually IRTF is a related organization to IETF. Internet Engineering Task Force and Internet Research Task Force. So Internet Research Task Force has a working group on quantum internet now, and they are trying to start a kind of the standardization related work on quantum internet. And so this is the first published document by IRTF, architectural principles for quantum internet. So actually this is like a kind of the guideline of architecture, how to design quantum interconnector internet architecture. And this is a kind of guideline to connect physicists and network engineers. And yeah, so this kind of work also has started for quantum internet as well. Yeah, so our standardization document, so 9340. So until 9339, so they are all classical network standardization or related documents. And so, yeah, so summary of this talk. Yes, so we have worked on both of quantum data center area network and also quantum internet size network as well. And we now we have the implementation of quantum interconnect for data center area network, and we are expanding that network to quantum internet. And I think, so those two things, the actual implementation in real testbed is of course important, but it is limited to small scale. So simulation to evaluate that system, that architecture protocol in large scale network is also important. So those are two pillars. And we are implementing our network systems, especially softwares, and so we are making them available online. So please use that. And finally, we are proposing the Q-Fly quantum interconnect. So it involves the quantum link architecture, quantum link implementation, and also the multiple group connection. So for scalable quantum connection between arbitrary pairs of quantum computers. Okay, now thank you so much. Questions, discussions? Yes, Bill.
I'll start with the provocative one. I'll start with the provocative question. Why are we standardizing now when we don't even really have big networks? The internet is a network of networks.
Yes.
Given we don't know how a quantum network works, I mean, you've done some design principles there.
Oh, yeah. So actually, yeah, so the physical layer, so there are still many fundamental research we have to conduct.
What about quantum switches?
Quantum switches.
So we don't even know the components.
Yes.
We know some of them, but we don't know all of them. So all I'm saying is, at the moment, you're trying to standardize something that doesn't exist, that we don't know the operating principles on.
No, they exist now. We made it. Sorry. Anyway, yeah, Bill is right. There are so many things we are not sure, but the hardware implementation there are many spaces to work on. But so let's think about the management layer of quantum networks. So we can start to design protocol, and we can discuss what protocol is good. So now this is related to the standardization work. So yeah, and actually in classical, I think the same thing with classical network will happen, I believe. So in classical network, so this is the layer architecture, protocol stack of classical network. The number of protocols standardized actually used in classical network is so many physical layers, so many data layers, but only one or two, so small number of networking layer. So the internet uses only IP, internet protocol, right? So this is required to connect all the network all over the world. And the transport layers, so now a bit more protocol works compared to the network layer. And we know so many application layer protocols in classical networks. So the number of the protocol is like this shape. So the same thing will happen in quantum networks as well, I expect. So there are so many candidates of the physical implementation of quantum networks. So it will lead to so many numbers of physical layer protocols in quantum networks. But in network layer, to make a global quantum internet happen, only one or two, so two, I mean, IPv, in classical case, IP version 4 and IP version 6. So they work together. So anyway, so small number of network layer protocol can be permitted. So this kind of standardization can start. So not in physical layer, but but upper layer, so middle layer can start, I believe, and so it will help the implementation of physical layer protocol. So because we can, so I mean to have a same network layer protocol, so it will a kind of the standardizing the evaluation protocol of the physical layer. It will work like that. So that's why the standardization work is already important for quantum networks. Okay, thank you. Yes.
Distributing the quantum computing or quantum computation or quantum circuit, there were always the entangled gates and the entangled bits and stuff. And we simply like map it on the coupling graph map and try to
Mapping on what?
map these onto a graph network, like whatever, we map it and try to optimize and reduce the connections. So like okay, for the optimization stuff is okay, but for the physical stuff, these links kind of reduce or kind of touch. Doesn't it affect the final output of the network? For simulation based, it kind of gives a good result, like we are using less number of qubits and this stuff. But physically, does it also implement in a similar manner? Or like, because see, there is a gate that is a 2-qubit gate. You distribute those 2 qubits to 2 different QPUs. You have to apply an entangled gate in this, correct?
Yes.
Physically, it becomes a very difficult task.
Oh yeah. So do you mean to connect heterogeneous QPUs?
Yeah.
Oh yeah. So that must be a very tough work, hard work, of course.
Just simulation based.
Now actually we haven't worked on the different type of heterogeneous QPU types yet. That must be tough because the frequency of Rabi oscillation is different, and so there are many physical properties are different. So to connect such QPUs will be so tough work.
During partitioning the actual problem, the quantum problem, what constraints or what parameters do you have in mind so you can partition it in such a way that it doesn't change the output?
So yeah, actually, I have no idea about that yet. So yes, but to connect different types of the technologies, physical properties must be big hurdle, and also the management part there will big hurdle as well, because the difference of the the synchronization is also difficult for different types of the qubits, because the lifetime of them differs so largely, and the gate duration is different as well. And for protocol, the capable tolerable latency of protocol is also different. So many things are so different. So we have to consider deeply about that. So, but yeah, I think it will happen after we standardize a quantum communication protocol for homogeneous connection. So beyond that, we have to think about that more seriously. Does this answer your question? So any other questions?
No more questions. I would like to thank Shota.
Oh, yeah, thank you so much.
And let's
OIST shirts. Great. いいね。
So Shota is leaving today, so if you have any questions online or offline, please reach out to him because he leaves.
Yeah, sorry about that. I came today and I have to leave today.
You're a businessman.
Kind of. Okay, thank you so much.